So in this lecture, we will continue discussing about caches. In the last lecture, we discussed about various types of mappings that are possible in the form of direct mapped, fully associative cache and KOA associative caches. So in today's lecture, we'll jump a bit deep and try to understand what kind of misses are possible in caches, how to deal with the misses, and how it affects the performance. So our caches are of limited size and limited associativity and fixed block size. It's bound to happen that we'll get some misses. We may not get cache hit all the time, unless our the data footprint is pretty tiny, and that is kind of fitting into the cache. So there are basically three kinds of cache misses, which are also known as the 3C misses. Although there is another C that is coming in multi-code, but for this lecture we'll stick to the first three misses. So the first one is known as the cold miss or the compulsory miss, and this happens because when you boot up your system, your cache contains nothing. Remember, these are volatile memory. They don't store data once you power off your system. So the very first access to any particular address will get you a miss, and that is the cold miss or compulsory miss. Then we may get misses because of the conflicts, and the conflicts may happen because multiple addresses are getting mapped to the same set, right? So if you remember our lecture on associative caches, we talked about 2-way associative, 4-way associative, or k-way associative cache, which means at a given point of time we can allow maximum k lines that are mapped to the particular index, right? If there are more than k requests which are mapping into the same set, then obviously there will be a miss, and that miss will be known as the conflict miss. And finally, as our cache sizes are fixed and it may not be sufficient for all the programs in the world, we may get a miss because of the size constraints. Okay, so these are typically known as the 3C, three kinds of cache misses. We will look at how these misses will be affected based on our design parameters, the various knobs that we discussed in the last lecture. So, but first thing is, whenever we get a miss, we need to replace a block. Replace is also known as evict a block, right? Because you are dealing with a fixed size cache or a fixed set for a given index, and the moment we get a miss, to accommodate space for new data or the new address, we need to replace the existing one, right? So it's like if you have a k-way associative cache, that means you have k lines in that particular set, and all of them are full, right? Then if a new request comes, it gets a miss. Let's call it as a conflict miss. So now we need to decide which of these lines to replace or evict, so that we can provide space to the upcoming block. So various policies can come into picture here, and then they will have their own utilities. But theoretically, the best policy is what is known as the Beladis optimal policy. You may have heard about it in your OS course. So the idea is pretty intuitive. It says that you replace a block that will be used furthest in the future, right? So if you have k blocks here, it says that you should replace the block that will be used furthest in the future, right? So that means there is no near reuse at this moment. But for that, you need to know the future of all the blocks that are present in a particular set, which is not practical, it's not feasible. We don't know how things will look like, right? So that's why the architecture community tries to come up with heuristics that can provide performance closer to Belady, and if not the actual Belady's policy. So at a top level or at a high level, this notion of replacing a block is actually known as something called a replacement policy, and it's actually a collection of three sub policies. So one is the eviction and replacement. When you get a miss, which block to replace, assign a priority and decide. When you insert a block from the memory, because on a miss, you will evict something, evict the old one, and bring something new, right? Where exactly you will put it? What will be the priority in terms of the eviction policy, right? And then once the block is there in the cache, if it gets a hit, what will be its updated priority? Okay, so let's understand that through a simple example. Let's talk about least recently used policy or LRU policy that kind of evicts the block which is not recently used. Okay, so and then we'll have priorities for each block. Whichever block is placed in the, let's say, LRU position, that will be kicked out. So pretty simple. As I have mentioned, the eviction policy decides which block to evict or replace. So if we have a LRU based priority chain, if we have number of blocks for a given set, what it does, it assigns priority for each block. Let's assume that some block will be MRU, some block will be LRU, and some other blocks will be roaming around in between the MRU and LRU positions, right? So the replacement policy will kick out the block which is present in the LRU position. Okay. Then comes the insertion policy, which says when a new block comes into the cache, where exactly will it be placed? Whether it will be placed in the LRU position or in the MRU position or in somewhere in the middle, right? So the typical LRU policy actually inserts a new block at the MRU position because that's the most recently used. MRU stands for most recently used, and the new block is actually the most recently used. So that will kind of update the priority chain that a particular cache set is maintaining so far, right? The third policy or sub policy is the promotion policy, which says once the block is there inside the cache, what happens if you get a hit? Let's say you get a hit again, right? So which means this is the most recently used block, so you should put it in the MRU position. So for example, if block number E gets a hit now, so E will move to the MRU position, right? So E will come here, I will get shifted, A will get shifted, B will get shifted, C will get shifted, and D will get shifted, right? So that's how the priority will be, right? And so these are the three sub policies. When they work cohesively, that becomes a cache management policy. So LRU policy is good as long as you have locality that can be preserved with this heuristics that is kind of assigning priorities for each block based on the recency. So for example, if you have a 16-way cache, you will need 4 bits per block. Okay, that 4-bit will actually signify what is your position in terms of MRU or LRU. So for example, for MRU you can say 0000, and for LRU you can say 1111, right? So this is for a 16-way associative cache, right? So any block that has a value 1111 will get replaced, right? So that's the eviction policy. So LRU does well, but for most of the applications, but whenever the working set of the application is greater than the cache size, that means the data footprint is greater than the cache size, then LRU causes thrashing. And thrashing actually makes the effectiveness of cache pretty minimal as you get more and as you will get more and more misses. Okay. So these are typical kinds of applications that you will find. So something is cache friendly application of workload, which means once you increase the cache size, the miss rate goes down, right? So this is the plot. And if your working set is already fitting into the cache, so that's the cache fitting workloads. So this is an example. Let's say you are using a 4 MB cache and your data footprint is also 4 MB. So you won't get any misses after that. Thrashing is a workload whose working set is much greater than the cache size. Let's say your cache size is 4 MB, and even though you are increasing the cache size, the miss rate doesn't improve significantly. Suddenly, after a point, the miss rate goes down to almost 0, right? So that's kind of the working set of that particular workload. And finally, a streaming workload where no matter what you do, you will get misses because there is kind of no reuse. Okay. So irrespective of cache size, the miss rate is kind of a constant here. Okay. So as I mentioned, LRU is kind of not effective, and in the current context of multi-cores, though we haven't discussed what exactly multi-core is, you can assume that in a multi-core system, multiple cores share a cache, and that's the L3 cache, which is known as the last level shared cache, and the effectiveness goes down, especially in the shared caches. So recent commercial machines use a policy called RRIP based policy. We will go through that at a high level here, which is called the Rereference Interval Prediction Policy. So what it does, instead of having a MRU and LRU priority where you need 4 bits per block, it actually groups blocks as per their reuse, right? And it creates kind of 4 groups. You can say that 00 is it will be reused just now, and 11 they won't be reused even in the near future, right? So the blocks with 11 are the candidates for eviction. Blocks with 00 are kind of cache friendly blocks. Okay. So this is what it does. It kind of divide all the blocks in the form of this re-reference interval prediction values, where it predicts the values or predict the blocks into 4 different quadrants, right? So in terms of reuse, whether the block will be reused or not. So near, immediate, far, and distant. So in this in the form of counter values, you will have something like 00, 01, 10, and 11, right? So for a RRPV value of 2, you will have 4 values, and on a miss, you will actually evict one of the blocks that has a value 11, right? So the beauty of this policy is, irrespective of your associativity, the storage overhead is constant. You need just 2 bits per block, right? Even if you go for 16-way associative cache, you don't need 4 bits per block, right? So this is the overall idea, where, as I have already mentioned, you kind of evict the block from distant RRPV values, and whenever you kind of get a hit to any block, that's the promotion policy, you make it 0, okay? But you insert a block, you insert at a middle zone, kind of, where you kind of assume that, yeah, the block will be used in future, but we don't know whether it's in the near future or far future. But if it gets a hit within its lifetime in cache, then it gets promoted to the near immediate quadrant. Okay, so that's the high level view about this policy called RRIP, which is re-reference interval based policy. Okay. So now let's redefine the cache misses, as we have already looked into the cache replacement. So the compulsory misses are the misses that would occur even with an infinite cache. Okay, because this is the first reference that you are making to any cache line, and obviously the address is not present in the cache, so you'll get a miss. And no matter how big is your cache, you will still get a compulsory miss. So capacity miss is kind of interesting. It says, even if you have a perfect Bellardi replacement policy, you will still get a capacity miss, right? So as I've mentioned in the initial slides, that capacity misses are the misses because of the size constraint. And one way to quantify that is, if you are getting misses even with a perfect replacement policy, then that's the capacity miss. Okay. And conflict misses. So if you come up with an ideal fully associative cache, then conflict misses will be 0, ideally 0, right? So these are the different ways to look at the misses that we have already discussed. So let's look at how different cache knobs affect these misses. So for example, cache size. If you have a larger cache size, it reduces capacity, which is a good thing, and it will reduce the conflict misses overall if you look at the global picture. But hit time will increase. The time to compare your tags and then extract the block will increase, because the number of blocks will be higher, and then depending on the associativity, even the number of comparators will be more, right? If you increase the associativity, again, it reduces the conflict misses, pretty intuitive, but it will again increase the hit time, because you are increasing the associativity. You need more comparators for your tag comparison. Finally, if you have a larger line size or a block size, it helps removing some of the compulsory misses, right? Because imagine a block size of just 64 bytes compared to a block size of, let's say, 1 GB, just an extreme example, right? Or let's say 1 kilobyte. So which means in one go, you're kind of preloading all the data into the cache, and that kind of eliminates the compulsory misses. Even if you are accessing a particular address for the first time, you will still get a miss. The obvious downside of this is it will increase the miss penalty, right? So bringing out a 64-byte block from the memory is kind of cheaper compared to bringing out 1 KB block in one go, right? So these are the trade-offs that you can actually think about what happens when you change these knobs. So when we look at the line size, right, usually the trade-off is between how much bandwidth or energy you are consuming, right, and what's your hit rate, right? So you will kind of get a sweet spot where you kind of exploiting the spatial locality properly, right? And at the same time, you are not consuming additional bandwidth and energy, right? So you can't have a small block or a small line, okay, because that will affect your locality and other things. You can't have a large block also because that will affect the other bandwidth and energy consumption, right? So you need a sweet spot that you have to determine empirically for a set of workloads that you are interested in. Similarly, cache size, it's depending on the application that you are using. As long as you are kind of making sure that the working set fits into the cache, then that will be the ideal cache size, right? After that, you won't get much improvement in terms of hit rate, right? Till that point, you are getting improvement in hit rate because the working set was not fitting into the cache. So working set is nothing but your data footprint at a given time interval. We are not talking about the data footprint of your entire application. You may be using 9 GB of data, but in a short interval, how much data you are using, whether it's like 4 MB, 32 MB, 16 MB, or whatever. So based on that, your cache hit rate will get affected. Okay. Finally, associativity. Though this plot shows the trend between hit rate and associativity, another crucial point is hit time, right? If you increase the associativity, the number of comparisons will go up, and that will increase the hit time. So that's why at the L1 caches, which are the smaller ones closer to the processor, you will find that the associativity is relatively lower compared to, let's say, last level L3 cache, right? And one thing that you should keep in mind is associativity should not be power of 2. Okay, it's kind of a myth if you are like aware of some articles or some books which talks about that, but you will find commercial machines with associativity which is not in the power of 2. Okay, so with all this trade-offs that we have discussed, we should have a metric that says how good is our cache for a given application or a given workload. So you can debate about hit rate, or you can debate about the other way in terms of miss rate. But usually these metrics are actually not good enough. And why it's not? Because hit rate doesn't differentiate between 1 by 1 versus 1000 versus 1000, which means the new numerator is number of hits and the denominator is number of accesses, right? So if your number of cache hits is 1 and the number of accesses is 1, it says the hit ratio or hit rate is 100%. It does the same for 1000 accesses, and it will do the same for 1 billion accesses, right? But if you look at from the IPC or the CPI point of view, the utility of hit rate 100% in this condition will be almost negligible. However, if you look into a cache where 1 billion accesses are getting 100% hit rate, so this will affect your CPI significantly, right? So instead of looking at hit rate and miss rate, usually the community uses a metric called misses per kilo instructions, which means if you are running a out of order superscalar processor, out of every 1000 instructions, how many misses are you getting at a particular cache. Okay, so this is more reasonable approach when it compares to comparing performance of caches. Okay, now the previous slide talks about comparing or understanding the trend in terms of whether a cache is doing good or bad. But if you look at finally, we are always interested in reducing the CPI, right, or improving the IPC. So for that, we need to deal with the number of cycles, right? So the C and CPI and IPC are the key because the instructions remain the same, right? So for that, for a given cache hierarchy or memory hierarchy, there is a term called average memory access time. It says on average how much time it takes for a particular load to get the data, right? So if you are in the let's say vanilla 5-stage pipeline, you are getting a load instruction and you are demanding the data in the 4th stage, how much time it's taking. So if you have started your request at time t and you are getting a response at t plus delta, so that's kind of your memory access time, right? So the way to quantify this is for each cache, you find out what's the hit time, where you kind of compare the tag, compare the index bits, get the data. That's the hit time, right? If you get a hit, that's all done. That's the access time. But if you get a miss, find out what fraction of accesses are missed. That's nothing but the miss rate, and what's the penalty associated with that miss. So if you multiply a miss rate with miss penalty, that gives you the entire access time on top of hit time, because hit time will be there irrespective of hit or miss. You have to first compare to know whether it's a hit or miss, right? So you can actually extrapolate it to a multi-level cache hierarchy. For example, if you have a 2-level cache hierarchy, so you can say hit time of L1 cache plus miss rate of L1 into miss penalty of L1. So let's say hit time of L1 is 1 cycle. Miss rate of L1 is, let's say, 0.5, 50% of the time it misses. Now miss penalty of L1, now it is dependent on the next level of cache and memory, right? So miss penalty of L1 will be nothing but hit time of L2, next level, and miss rate of L2, let's talk it like 0.2%, and miss penalty of L2, right? So this is kind of a recursive definition that you can think about that's going through the entire memory hierarchy, right? So ideally, we need pretty competitive hit time, that it should be low, even the miss rate should be low, and the miss penalty should be low. So these are the 3 ideal conditions for any cache or cache hierarchy. So ideally, you should have a miss rate of 0.00%, right? Which means there is no miss penalty involved because there is no misses. Only the hit time is there, and let's assume your hit time is just 1 cycle. So that means all your loads that are stuck in the memory stage, you will get the data in 1 cycle. But as we have already seen, that's not the case in a real system, and it can go up to 100 or thousands of cycles, right? So with that, I will stop and we'll continue discussing some other aspects of caches in our next lecture. Thank you.